Hello everyone, it's the Metalist Programmer here. Today I want to show you some tests that I've done with various single board computers and the results that I've had. Normally I don't do this sort of videos on my channel, on this channel at least, where I deal with hardware equipment. This channel for the most part will be dedicated to software and particular to the various languages that I'm currently building. But since I had to do some tests for myself recently, I thought why not make a video, share what I've done and the results that I've got with you. Hopefully this will help some of you that might be interested in the same subject. So what I've done is basically I've taken various single board computers that I have and that I've bought in the past, and I've put them to the test, at least to a few simple tests. I want to buy some more, and I do not know exactly well, I have some requirements, but of course I do not want to spend more money than I need to. So I wanted to know which of the a few models of single board computers perform the best in terms of computations per second, and also compare those performances with the price that they have. I am particularly interested in single board computers that have a SATA connector, so that I can connect SATA hard drives, because I have quite a few of them, and I want to make multiple storage devices that can also do other things. Okay, so I have put several let me switch to desktop. I have put several of these boards to the test, and I will explain them to you one by one today. But first, let me explain to you quickly the tests that I've made. So I've made a simple, relatively simple program in C++. It's not great. It's a quick and dirty solution. I haven't written C++ code in quite a lot of years, so I may be a bit rusty about writing my C++ code. But anyway, I wanted to test and see in actual numbers how many operations per second can these processors do, all the processors of all these single board computers. I wanted to get an idea of how many operations of adding two numbers, subtracting two numbers, multiplying, dividing, and a few other things can these processors do. Because ultimately, what we do in any programming language will be translated into machine codes that essentially this is what all that machine code does. Load some variables in some computer registers, perform some mathematical calculations with them, pushes the results into other places, and so on and so forth. So I wanted to test integers, floats, and doubles, and for each of them I wanted to test the mathematical operation of addition, subtraction, multiplication, division, and I also wanted to test some binary operations, binary shift, AND, OR, and XOR, exclusive OR. So basically for each of these tests I have a function that I have called this function does her best to provide me with this number of computations per second. So let me just quickly show you the general idea of these functions. Each function will be slightly different based on what she needs to do. The addition functions are the simplest. I'm basically I'm creating a variable, an integer variable that can go from 0 to the maximum value. Integers are typically stored on 32 bits. So I'm essentially counting from 0 to the maximum value that I wrote here as a hexa value. And I am measuring the time that it takes for these increment operations to happen. An increment operation is basically adding 1 to the existing value, right? So in this way, I'm testing the adding of two integers of 32 bits each. By having a clock start and a clock end value, I can then make the difference and obtain the difference in clocks, and then I can convert this difference by dividing this to a constant named clocks per second in order to get how many seconds did this time meant, because without referencing this to clocks per second, I only have a difference of clocks, of clock ticks. So of course that wouldn't help. And once I get basically the amount of time that these operations took in seconds, then I can simply divide the number of operations that have occurred in this time to this amount of time, and this will be the number that I will care for, the number of operations per second. Okay. So for integers, for adding integers, is very simple. Like I said, we increment from 0 to the maximum value, which is approximately 4 billion. This will also be the number of iterations, so the number of computations that the processor will do. If we divide this to the number of seconds that have elapsed, we get the number of integer additions per second. Same thing I want to do with 64-bit integers, because 64-bit integers, in general, 64-bit variables are more difficult, and on some platforms are not native. So I want to see how much slower is adding two 64-bit integers compared to two 32-bit integers. Okay, and the algorithm is the same, more or less the same for a floating point, except instead of adding 1, I'm adding 1.2, so that I have a floating point value. And similar things happen to subtraction and division, multiplication and division as well. Multiplication is slightly more complex, because I have to multiply an integer with something that is not 2, 4, 8, 16, 32, and so on, because then the compiler will change my my operation from a multiplication to a bit shift one. So I chose to multiply an integer starting from variable from the value 2 with a constant 3, and I'm stopping at some point before the integer overflows. I'm counting how many iterations I have made. I am doing this 1,000 times, and well, in the end I have a complete count of iterations, and I'm calculating the time that it took for these iterations to happen. Something a bit more complex happens with multiplication of 64-bit integers, because since I will have a certain number of so with 64-bit integers, I'm doing something similar, but I'm starting with number 3 I'm multiplying that by 3 every single time, every loop, and essentially what I'm getting is in the end is 3 raised to a certain power, enough to get me in the end to this constant, which is 18 million billions, something like that, which is pretty much the last integer value that can be, at least the last unsigned integer value that can be stored on 64 bits. And in order to I cannot basically I can't really, and I'm also doing this a million times, okay? So I had to calculate in reverse how many iterations there will be in total, and I have determined mathematically that there will be approximately 40 million iterations. So knowing this, I'm dividing this number of iterations to the time that it took for them to execute, you know, and this way I get the total number of computations per second. And something similar happens to floating point multiplication, double multiplication, and something similar to division as well. So these are pretty much the tests and the way I perform these tests. Of course, since in each loop I am not just able to, I'm not able to just have that particular operation that I want to measure the time for. I will also have some other operations, like you know, a while loop has to check every single time if the condition is satisfied. So when I'm setting my clocks, clock start and clock end, you know, these and then calculating the time difference, this time difference will always include the time that it took for the processor to also make this comparison, and maybe even other operations, like for instance a count incrementation. Okay, so we will not get a 100% accurate number of operations per second for that particular operation alone. However, I do not care about this that much. I don't care about absolute values in the end. I care about having some values that I can compare one board with another. Okay, so this method of testing is good enough for me. And now let me show you the results, because I have tested multiple. Let me show you a few other things before. So this whole idea started with me having bought in the past a Banana Pi M2 Berry board made by a Chinese manufacturer called Sinovoip. Now, these Banana Pi boards seem to not be very popular amongst electronic distributors, and especially this particular distributor. And by the way, I'm not sponsored by anyone, so I'm not trying to advertise anyone. I'm just trying to be useful to you. This particular distributor still has a certain number of boards from the Sinovoip company. However, he seems to not want to work with them anymore, because for all these boards, you will see a message, product available until the stock lasts. So basically, once these will be sold completely, this distributor will not want to replenish the stocks by, you know, placing new orders to the manufacturer and buying some more. Which is a shame, because many of these banana boards have a SATA connector. Okay, if I show you the big image, you see here a SATA connector, and that's very useful when we want to connect a hard drive. And honestly, I think in most cases we will want to connect a hard drive to a single board computer for one reason or another, but there will be many cases many times when we will want to have a large storage device attached somehow directly to our single board computers. Sadly, this is not possible with the Raspberry Pis. Raspberries do not have anything like this. Apparently, the Raspberry Foundation is not interested in making any new model with a SATA connector or something similar. Anyway, these boards are the cheapest. These Banana Pi M2 Berry boards can be still bought at a price of 20 euros, including VAT. And so this made me want to know, before I actually place an order and buy some more of these boards, how good are they? What is their overall performance, especially compared to others? And a few other boards that I've managed to test meanwhile: Banana Pi M2 which is a quad-core board that wants to basically compete with Raspberry Pi Zero. This product is no longer available to this distributor. And then a couple of boards made by Olimex, which is a Bulgarian manufacturer, A10 Olinuxino and A20 Olinuxino. These are boards that use the all-winner A10 and A20 respectively. These are two models of processors made by the Chinese manufacturer all-winner. All these Olinuxino boards also have a SATA connector. I know it's not very clear, but let me show you in a moment after this weird animation is done. Here we see that on one side of this board, and the same is true for the other model of the board, we have a SATA connector next to HDMI and next to I think USB is this one and whatever else. So these boards can also be connected to a hard drive, and we can create a storage device with them. However, as I will show you in a moment in the tests that I have done, this Banana Pi, sorry, not this one, Banana Pi M2 Berry is more powerful than both A10 and A20 Olinuxino, and is also cheaper. Okay, this is 20 euros, A10 is 35, and this one is 50. A20 Olinuxino is 50 euros. So there are significant differences in prices. Hence my desire to test them to see, how good they are. Anyhow, so without further ado, let me show you the results. So the program that I've shown you earlier, I've shown you the source code, performs tests on a single core. I did not want to bother with creating multiple core tests. It would have been harder, and I didn't care. My logic was that theoretically, if a single core is able to compute a certain number of operations per second, then each core is able to do the same number. So we will just simply multiply the number of cores to the performance tested on a single core. Okay, this is not 100% true, but yeah, for the most part, this is a simplification that I wanted to make so that I don't bother with anything more advanced and more difficult. Because again, I wanted to test these quickly. It still took me about 2 days or more than 2 days to set up everything and perform the tests. So I've made these tests. I basically have 4 tests for adding numbers: integer 32-bit, integer 64-bit, floating point, and doubles. The same 4 tests, but for subtracting numbers, the same 4 tests for multiplying two numbers, the same 4 tests for dividing numbers, and binary shift left right at the same time, binary AND, binary OR, binary exclusive OR operations. And the numbers that we see here are in millions of operations per second. Okay. If I am to just one moment, if I am to show you how the software runs on my computer, okay, it basically opens a console window and starts to perform the calculations, and from time to time spits results on the screen that are nicely formatted with dots every 1,000, so as 1,000 separators, so that we can see clearly, you know, what numbers are we talking about. And after I've done all the tests for all the boards, you know, I have copied these values. I have extracted only the millions of operations, because I don't care about super precise values, and I have placed them in these Excel files. All the blue columns are essentially these tests multiplied by the number of cores that every board has, because of course in the end we have to calculate the processing power of the entire board with the processor that has all the cores. Okay, so for this oversimplification, I simply multiplied the results I got on one core with the number of cores, and I got the final numbers that I could then compare. I discovered, which wasn't a surprise at all, that Raspberry Pi from the first model was the least performant one, the board that has the smallest performance. And it's understandable, since Raspberry Pi from the first generation is the oldest one, right? So these are all the boards that I have had and I have tested. I have Raspberry Pi 1B+. I do not have a Raspberry Pi Model 2. I never bought Model 2s back then when they made them. I have a Raspberry Pi 3B, a Raspberry Pi 4, and a Raspberry Pi 5 as single board computers of this particular size. Then I have a Raspberry Pi 0 and 02, which are the smaller versions. And then the other boards from the other manufacturers. Banana Pi 0, Banana Pi M2 Berry that I've shown you earlier in pictures on the website. And then Olimex A10, Olimex A20. Now, after obtaining all of these values and calculating by extrapolation the other values that we care about, I had to take one of these boards as a reference point and then calculate all the others relative to this board as reference point. And since Raspberry Pi 1B is basically the weakest board, I chose to take this board as a reference. So I've made another table, okay, where I've put the absolute value on a separate column that is associated with Raspberry Pi 1B. Therefore, all the results for this board become 1, mathematically 1. And then all the results that here are in blue columns mostly, divided by these reference values, become every other column for every other board. Okay, so this is a process that's called normalization in mathematics and engineering in general. Okay, so I've normalized all of these values so that we get to see each board how much more performant or less performant she is relative to Raspberry Pi 1B. And because this is still difficult to see and to assess, basically, because, you know, we still have some numbers. It's not all that easy to tell results from a table. I have made some graphics. Graphics are much easier to see and to understand, okay? So essentially on the x-axis I have this entire list of tests that my Excel did not place as text labels, but actually associated some bogus numbers and placed those numbers on the x-axis. But we don't care, it doesn't matter. On the y-axis we have all of these values, and because there are pretty big differences between some values, I chose to make the y-axis logarithmic, okay? So this line over here, which also represents the Raspberry Pi 1B results, is the line with value 1. This line over here is 10, this line over here is 100, and so on and so forth. So basically, okay, you have a logarithmic scale that is able to display a lot easier these results. And this way we get to see even big differences between boards. So I don't think it was a surprise for anyone to see that Raspberry Pi 5 is by far the most performant board, at least in terms of processing power. He has the most processing power out of all of these boards by quite a long range. So if we are comparing Raspberry Pi 5 to Raspberry Pi first generation, then we get to have on average at least 80 times more processing power, and in certain situations we even get to have 300 times more processing power, or even 400 times more processing power than the first generation Raspberry, and is the most performant board. Next one after Raspberry Pi 5 comes Raspberry Pi 4, which was kind of expected. Raspberry Pi 4s are also very powerful. They have been designed to be powerful, so that doesn't really surprise me. Then the good news is that we have a whole bunch of boards that have roughly the same processing power. Amongst them is the Raspberry Pi 3 and this Banana Pi M2 Berry, Banana Pi 0 M2. Okay, these boards all have the same rough processing power, and they are also pretty similar to Raspberry Pi 02. There has been only one case where Raspberry Pi 02 has shown a lot more processing power than these other boards and has come closer to Raspberry Pi 4. But this is just an exception to the rule, and it's quite a strange one. So if we are to take a look at so what is it? Raspberry Pi 02. Okay, so this column. If we are to take a look at this column, we see that this particular line, which represents the number of integer 64-bit divisions, has had a very big number of computations per second from my tests. And this is the point where you know, we have here these spikes. Apparently these boards are very good at dividing two numbers stored on 64 bits for some odd reason. They do this a lot better than other operations, but anyway, for the most part Raspberry Pi 0 is as little or as much as powerful as Raspberry Pi 3, Banana Pi M2 Berry, and Banana Pi 0 M2. Again, this for me was a very good news, because I want to buy more Banana Peas M2 berries that have a SATA connector, and to know that they are as powerful as Raspberry Pi 3s is a good thing. What was a disappointment were the other boards. So Olimex A20 is significantly weaker than these other boards. Olimex A10 has moments, has various tests in which he was weaker even than the first generation of Raspberry. This is why the test looks like a weird sinusoidal wave, because some of these tests performed have given me less operations per second than Raspberry Pi of the first generation was able to. So this was a very weird surprise. And the final board, Raspberry Pi Zero of the first generation, seems to be slightly more powerful than Raspberry Pi of the first generation, but not by a lot. Seems to be kind of on the same level. Of course, they are both single core processors, so doesn't surprise me. Yeah, so these are pretty much the tests that I've made and the results that I've obtained. Now I know for a fact what board makes sense and what board doesn't. Sadly, these Olimex Bulgarian boards are a bit too expensive for their performance, at least relative to the Chinese Banana Pi boards. They don't make much sense. So that's pretty much it. I won't keep you any further, since this is the end of all the tests and results that I've had. I hope they help you know a little bit better, if you are interested in at least these models of single board computers, which one to choose and what to expect from them versus others. I will I don't think I can place links on my YouTube channel yet, but I am placing this this link on the screen right now. You can show. Let me zoom in a little bit more so you can see this better. I have put the source code for this simple benchmark tool on my website at this address. If you are interested, you can, download him and compile him and play with him. So thank you very much for watching this video. I hope it helped you, and I will see you soon at something related to software engineering, computer programming, software in general. Thank you very much for watching. Bye bye.